In mathematics, the tensor product, denoted by ℕ, may be applied in different contexts to vectors, matrices, tensors, vector spaces, algebras, topological vector spaces, and modules, among many other structures or objects. In each case the significance of the symbol is the same, the freest bilinear operation. In some contexts, this product is also referred to as outer product. The general concept of a tensor product is captured by monoidal categories. That is, the class of all things that have a tensor product is a monoidal category. The variant of ℕ is used in control theory. Tensor product of vector spaces. The tensor product of two vector spaces V and W over a field K is another vector space over K. It is denoted VH, KW, or VH, W when the underlying field K is understood. Equals prerequisite, the free vector space equals, the definition of ℕ, requires the notion of the free vector space F, S, on some set S, a vector space whose basis is parametrized by S. By definition, F, S, is the set of all functions f from S to a given field K that have finite support. That is, f is identically 0 outside some finite subset of S. It is a vector space with the usual addition and scalar multiplication of functions. It has a basis parametrized by S. Indeed, for each S in S, let Is, Sk be the function given by Is, S, equals 1 and Is, T, equals 0 for any Ta permel S then ISS S is a basis of F, S, since each element of F, S, can be uniquely written as a linear combination of IS's. Because of this explicit expression, an element of F, S, is often called a formal sum of symbols in S. By construction, the dimension of the vector space F, S, equals the cardinality of the set S. Equals definition equals, given two vector spaces V and W over a field K, the tensor product U of V and W, denoted as U equals VH, W is defined as the vector space whose elements and operations are constructed as follows. From the Cartesian product via W, the free vector space F, via W, over K is formed. The vectors of VH, W are then defined to be the equivalence classes of F, via W, under the following equivalence relations. The operations of VH, W, that is the map of vector addition plus U and scalar multiplication K U are defined to be the respective operations plus F and F from F, via W, acting on any representatives. In the involved equivalence classes outputting the one equivalence class of the result. The result is independent of which representatives of the involved classes have been chosen. In other words, the operations are well defined. In other words, the tensor product VH, W is defined as the quotient space F, via W, /n, where n is the subspace of F, via W, consisting of the equivalence class of the zero element, n equals, A and F, via W, under the equivalence relation of above. The following expression explicitly gives the subspace n. In the quotient, where n is mapped to the zero vector, the following equalities all hold, which is exactly what is desired. In these latter expressions, the, etc., are images in the quotient of vectors in the free product under the quotient map. Usually, some other notation is employed for them, see below. Equals notation equals, elements of VH, W are often referred to as tensors, although this term refers to many other related concepts as well. If V belongs to V and W belongs to W, then the equivalence class of is denoted by VH, W, which is called the tensor product of V with W. In physics and engineering, this use of the ℕ symbol refers specifically to the outer product operation. The result of the outer product VH, W is one of the standard ways of representing the equivalence class VH, W. An element of VH, W that can be written in the form VH, W is called a pure or simple tensor. In general, an element of the tensor product space is not a pure tensor, but rather a finite linear combination of pure tensors. For example, if V1 and V2 are linearly independent, and W1 and W2 are also linearly independent, then V1 ℕ, W1 plus V2 ℕ, W2 cannot be written as a pure tensor. The number of simple tensors required to express an element of a tensor product is called the tensor rank, and for linear operators or matrices, thought of as tensors, it agrees with matrix rank. Dimension equals, given bases phi and we for v and w respectively, the tensors phi wj form a basis for v w. Therefore, if v and w are finite dimensional, the dimension of the tensor product is the product of dimensions of the original spaces. For instance, Rm Rn will have dimension Mn. Tensor product of linear maps equals, the tensor product also operates on linear maps between vector spaces. Specifically, given two linear maps S, via x and t, w or y between vector spaces, the tensor product of the two linear maps S and t is a linear map. Defined by. In this way, the tensor product becomes a bifunctor from the category of vector spaces to itself, covariant in both arguments. If S and T are both injective, surjective, or continuous, then S T is, respectively, injective, surjective, continuous. By choosing bases of all vector spaces involved, the linear maps S and T can be represented by matrices. Then, the matrix describing the tensor product S T is the Kronecker product of the two matrices. For example, if V, X, W, and Y above are all two-dimensional and bases have been fixed for all of them, and S and T are given by the matrices and, respectively, then the tensor product of these two matrices is. The resultant rank is at most 4, and the resultant dimension 16. Here rank denotes the tensor rank, while the matrix rank counts the number of degrees of freedom in the resulting array. A dyadic product is the special case of the tensor product between two vectors of the same dimension. Universal property equals. The tensor product is defined above as a universal property. In this context, this means that the tensor product is uniquely defined. Up to isomorphism, there is only one tensor product. In the context of linear algebra and vector spaces, the maps in question are required to be linear maps. The tensor product of vector spaces, as defined above, satisfies the following universal property: there is a bilinear map I via W of V W such that given any other vector space Z together with a bilinear map H via W of Z, there is a unique linear map H V W of Z satisfying H equals HAI. In this sense, I is the most general bilinear map that can be built from via W. In particular, this implies that any spaces with such a tensor product are examples of symmetric monoidal categories, as this is the defining characteristic of the category. Uniqueness of the tensor product means that for any other bilinear map I a squared via W of V a squared W with the above property there is an isomorphism K, V W of V a squared W such that I a squared equals KAI holds. This characterization can simplify proving statements about the tensor product. For example, the tensor product is symmetric, that is, there is a canonical isomorphism. To construct, say, a map from left to right, it suffices, by the universal property, to give a bilinear map via W or W B. This is done by mapping to W B. Constructing a map in the opposite direction is done similarly, as is checking that the two linear maps V W or W V and W via V W are inverse to one another. Similar reasoning can be used to show that the tensor product is associative, that is, there are natural isomorphisms. Therefore, it is customary to omit the parentheses and write V1 V2 V3 equals tensor powers and braiding equals, let n be a non-negative integer. The nth tensor power of the vector space V is the n-fold tensor product of V with itself. That is, a permutation I-florin of the set 1, 2. N determines a mapping of the nth Cartesian power of V. Defined by let be the natural multilinear embedding of the Cartesian power of V into the tensor power of V. Then, by the universal property, there is a unique isomorphism, such that The isomorphism I-florin is called the braiding map associated to the permutation I-florin. Product of tensors. For non-negative integers and S, a tensor on a vector space V is an element of. Here var is the dual vector space. There is a product map, called the product of tensors. It is defined by grouping all occurring factors V together, writing Vi for an element of V and Phi for elements of the dual space. Picking a basis of V and the corresponding dual basis of var, tar or S, V, is endowed with a natural basis. In terms of these bases, the components of a product of two tensors can be computed. For example, if F and G are two covariant tensors of rank m and n respectively, then the components of their tensor product are given by. Thus, the components of the tensor product of two tensors are the ordinary product of the components of each tensor. Another example, let U be a tensor of type with components e plus or minus I squared, and let V be a tensor of type with components var I cubed. Then. And. Relation to dual space. A particular example is the tensor product of some vector space V with its dual vector space var. In this case, there is a natural evaluation map, which on elementary tensors is defined by. The resulting map is called tensor contraction. On the other hand, if V is finite dimensional, there is a map in the other direction, where V1, Vn is a basis of V, and via is its dual basis. The interplay of evaluation and co-evaluation map can be used to characterize finite-dimensional vector spaces without referring to bases. Equals tensor product versus sum equals, given three vector spaces U, V, W. The tensor product is linked to the vector space of all linear maps, as follows. Here Hom denotes the K-vector space of all linear maps. This is an example of adjoint functors. The tensor product is left adjoint to Hom. Equals adjoint representation equals, the tensor may be naturally viewed as a module for the Lie algebra end, V, by means of the diagonal action. For simplicity let us assume R equals S equals 1, then, for each U in end, V, where way, in end, var, is the transpose of U, that is, in terms of the obvious pairing on V hash, var. There is a canonical isomorphism given by. Under this isomorphism, every U in end, V, may be first viewed as an endomorphism of and then viewed as an endomorphism of end, V. In fact it is the adjoint representation ad, U, of end, V. Tensor products of modules over a ring. The tensor product of two modules A and B over a commutative ring are as defined in exactly the same way as the tensor product of vector spaces over a field. Where now F, A, B, is the free R module generated by the Cartesian product and G is the A module generated by the same relations as above. More generally, the tensor product can be defined even if the ring is non-commutative. In this case A has to be a right R module and B is a left R module, and instead of the last two relations above, the relation is imposed. If R is non-commutative, this is no longer an A module, but just an abelian group. The universal property also carries over, slightly modified, the map IA, BA', are be defined by AA', B is a middle linear map. That is, it satisfies. The first two properties make IA a bilinear map of the abelian group A, B. For any middle linear map I of A, B, a unique group homomorphism F of A', B satisfies I equals FAI, and this property determines within group isomorphism. See the main article for details. Computing the tensor product equals, for vector spaces, the tensor product V hash, W is quickly computed since bases of V of W immediately determine a basis of V hash, W, as was mentioned above. For modules over a general ring, not every module is free. For example, Zn is not a free abelian group. The tensor product with Zn is given by. More generally, given a presentation of some module M, that is, a number of generators M, II together with relations, with, the tensor product can be computed as the following co-kernel. Here Nj, equals Aj a Jn and the map is determined by sending some n in the jth copy of Nj to a gene. Colloquially, this may be rephrased by saying that a presentation of M gives rise to a presentation of M Rn. This is referred to by saying that the tensor product is a right exact functor. It is not in general left exact, that is, given an injective map of the modules M1 or M2, the tensor product is not usually injective. For example, tensoring the map given by multiplication with n, z as z with zn yields the zero map 0, zn as zn, which is not injective. Higher Tor functors measure the defect of the tensor product being not left exact. All higher Tor functors are assembled in the derived tensor product. Tensor product of algebras. Let R be a commutative ring. The tensor product of the modules applies, in particular, if A and B are R algebras. In this case, the tensor product A'(R)B is an R algebra itself by putting. For example, a particular example is when A and B are fields containing a common subfield R. The tensor product of fields is closely related to Galois theory, if, say, A equals R, x, / f, x, where f is some irreducible polynomial with coefficients in R, the tensor product can be calculated as. Where now f is interpreted as the same polynomial, but with its coefficients regarded as elements of B. In the larger field B, the polynomial may become reducible, which brings in Galois theory. For example, if A equals B is a Galois extension of R, then is isomorphic to the adug, f. Other examples of tensor products equals tensor product of sheaves of modules equals tensor product of Hilbert spaces equals topological tensor product equals tensor product of graded vector spaces equals tensor product of quadratic forms equals tensor product of multilinear maps equals, given multilinear maps and their tensor product is the multilinear function, equals tensor product of graphs equals. It should be mentioned that, though called tensor product, this is not a tensor product of graphs in the above sense. Actually it is the category theoretic product in the category of graphs and graph homomorphisms. However, it is actually the Kronecker tensor product of the adjacency matrices of the graphs. Compare also the section tensor product of linear maps above. Monoidal categories equals, a general context for tensor product is that of a monoidal category. Applications exterior and symmetric algebra equals, two notable constructions in linear algebra can be constructed as quotients of the tensor product, the exterior algebra and the symmetric algebra. For example, given a vector space V, the exterior product is defined as. Note that when V's underlying field does not have characteristic 2, then this definition is equivalent to. The image of in the exterior product is usually denoted and satisfies, by construction. Similar constructions are possible for, giving rise to, the nth exterior power of V. The latter notion is the basis of differential n-forms. The symmetric algebra is constructed in a similar manner. That is, in the symmetric algebra two adjacent vectors can be interchanged. The resulting objects are called symmetric tensors. Tensor product of line bundles equals. Tensor product in programming. Array programming languages equals, array programming languages may have this pattern built in. For example, in APL the tensor product is expressed as. In J the tensor product is the dyadic form of /. Note that J's treatment also allows the representation of some tensor fields, as A and B may be functions instead of constants. This product of two functions is a derived function, and if A and B are differentiable, then A/B is differentiable. However, these kinds of notation are not universally present in array languages. Other array languages may require explicit treatment of indices, and/or may not support higher-order functions such as the Jacobian derivative. See also, dyadic product, extension of scalars, multilinear subspace learning, tensor algebra, tensor contraction, topological tensor product, monoidal category. Notes. References: Bourbaki, Nicholas. Elements of Mathematics, Algebra I Springer Verlag. ISBN 3-540-64243-9. Halmos, Paul. Finite-dimensional vector spaces. Springer. ISBN 0-387-90093-4. Lang, Serge, Algebra, Graduate Texts in Mathematics 211, New York, Springer Verlag, ISBN 978-0-387-95385-4, ZBL 0984.00001, Mr. 1878556, MacLean, S. Birkhoff, G. Algebra. AMS Chelsea. ISBN 0-8218-1646-2. Aguirre, M. Meyer John, S. Monoidal functors, species and Hopf algebras. CRM Monograph Series Vol 29. ISBN 0-8218-4776-7. Bibliography on the non-abelian tensor product of groups.